Good morning, guys. It is Tuesday, March 5th, 2019. I am going to be out today with a sick child, so I apologize. I do have her with me, so if you hear any coughing or weird noises in the background, that is probably her, so I apologize sincerely. But what I want to do is very quickly do a tutorial on molarity and dilutions, partly for those people that were out first and third yesterday, and for review for first and third as needed, but also for sixth period because I was supposed to be with you today. I apologize. Again, sick baby, so I won't even be doing the professional development class that I was supposed to be doing. For you guys to actually get the material. Thankfully, this really isn't too bad. It's just kind of a continuation of what we've been doing. So the first thing we're going to talk about is this idea of concentration. Okay, so concentration is probably a word you've heard of before, and we're talking about chemical concentration, not focus, like brain concentration. This is basically, in a very simple definition, how much stuff there is in a specific space. So it kind of sounds similar to density, which is how much grams there are in a certain volume. Kind of the same idea. There are several different types of concentrations. One of them would be density. You also have percent mass or percent volume. We will play with those at a later date if we get to them. They're exactly what they sound like. They're part over a whole, so it's the mass of a specific substance, such as like fluoride in your toothpaste. It would be the mass of the fluoride over the mass of the toothpaste, if you will, since that's what we're talking about. So like the whole toothpaste or the whole mixture or part of the mixture at least. Percent volume is the same idea. So those are commonly used in the industry for products that are being produced for the human population. You have parts per million, parts per billion, very commonly used in environmental science, especially for like water pollution or air quality. So parts per million is kind of what it sounds like. So if I have 5 ppm of, let's say, pollen, what that basically means is there's 5 pieces of pollens in a million pieces of air, if you will. So again, not something we use a lot in chemistry for any of these, though they can be depending on what type of chemistry you're doing. The one we will focus on predominantly in this class is molarity. Okay? And molarity is moles over liters. Okay? This is actually the standard unit of concentration in chemistry, and it is basically exactly what it sounds like. So instead of like density where it's grams per milliliter, which is looking at how much mass there is per volume, we're looking at how many moles there are per volume, which in terms of reactions, as you guys have been seeing as we're going through stoichiometry, is a more important value. And a lot of times as we're doing chemistry, we are dealing with solution-based chemistry, so molarity makes more sense to work with than grams. And so that's what we're going to do. And then tomorrow we're going to be combining and starting in molarity or even ending in molarity for our stoichiometry problems, for our limiting reactant problems. So this is, again, what I was telling you guys a while ago. We're not always going to start in grams. We can start in an infinite amount of units depending on what we're given, and we can go to an infinite amount of units depending on what we're given. So this is just kind of one of those add-ons, or plugins, if you will, I guess, that allows us to kind of move in and out of different units as needed. So, molarity, nothing more than a concentration. So think about making Kool-Aid. When you make Kool-Aid, you're adding a powder to water. If you add a lot of powder to water, you end up with a high concentration or a high molarity, if you will. Versus if you add just a little bit of powder to a lot of water, you end up with a low concentration or low molarity. We call something that is highly, that has a high concentration, concentrated, I know, shocker there, but something that has a low concentration is called dilute. We'll talk a little bit more about diluting stuff in just a minute. So molarity is actually pretty easy. It's just a plug and chug. It's an algebra equation, just like the same math you use in algebra. So let's kind of play with this for a minute. Let's say I have 15.8 grams of, let's say, sodium chloride, and I'm adding this to 565 milliliters of water. So basically, I'm going back to my stock room, I'm grabbing my sodium chloride out, I'm massing 15.8 grams of sodium chloride, and then I'm dissolving it in 565 milliliters of water. What is my molarity? Well, first off, we have to recognize that this moles is moles of the solute, which is who's being dissolved. So who's being dissolved is our sodium chloride. Okay. and this is our solvent, okay, and this is liters of our solution, okay, and I'll come back and explain that in a minute. So moles of the solute's very easy, straightforward. It's stuff we've been doing for a while now. So 58 grams, or 15.8 grams, sorry, is sodium chloride. We have a molar mass of sodium to be 22.99 plus 35.45 from the chlorine. So we have a molar mass of 58.44 grams for sodium chloride for 1 mole of sodium chloride. All right, so 15.8 divided by 58.44, and we get a mole value of 0.270 with proper sig figs moles of NaCl. Now, when we add this mass of sodium chloride to the 565 milliliters of water, our volume is not going to actually change. It's going to, basically the salt ends up filling the spaces that the water has, because water is a little bit spread out. So we end up with this idea that our solvent volume is going to be the same as our solution volume. So basically what that means is this is my volume of my solution, so what I need to do is get it into liters of my solution. Well, that's pretty straightforward. We know how to do that. We've been doing that for a while. We know there are 1,000 milliliters in 1 liter. And technically you don't have to show this work right now. I trust you guys are able to convert properly in terms of milliliters, liters, grams, milligrams, stuff like that. So you can just move the decimal if you want to. But either way, I get these two values. Now, molarity is moles over liters, so 0.270 moles over my liters, 0.565, and I just basically do that math. So 0.270 divided by 0.565, and I get a molarity value of 3 proper sig figs, because both of these have 3 proper sig figs, of 0.479 molar. Okay, so that's molarity. Not too shabby. Okay, let's look at another way to do molarity. Let's say the same problem. So I'm going to take the 0.479 molar solution, and we have 565 milliliters of it. And let's say I'm going to, actually, of that 565, I'm going to pull out 45.9 milliliters of it. Okay, I want to know how many grams, so this is just kind of another another molarity problem that you could see. Okay, so this is just kind of a continuation. So what do we do about this? Well, let's go back. Molarity is just an equation. Moles over liters. We know molarity is 0.479. We know our volume is 0.0459, because I just converted that to liters, over X moles. Okay. Well, we're trying to find grams. If we find moles of sodium chloride, could we find grams of sodium chloride? Well, yes. Yes, we could. We know how to do that. So we take 0.479 multiplied by 0.0459 for our volume, and we're going to get our mole values to be 0.0220 moles of NaCl. Okay, well, 0.0220 moles NaCl for every 1 mole of NaCl, because we're trying to go to grams. If we go back up here, what was our molar mass again? 58.44. 58.44 grams NaCl. So we multiply across. So in 45.9 milliliters of this same solution, we have 1.28 grams NaCl. Okay, so that is molarity. Pretty easy peasy. Now, with solutions, sometimes we're not given grams, or we don't have a solid that we can measure out grams in just as often water. Sometimes we have solutions that are already made that we buy from a company. So let's say in my stock room I have a 10.00 molar HCl solution. Well, I don't want you guys playing with a 10 molar hydrochloric acid solution. That's going to burn the crap out of your hands. Let's say instead I want to make it a 1 molar solution of HCl. Well, what do? I dilute it. And dilution, if that word sounds familiar to you, is basically making it less concentrated. Well, how do we make it less concentrated? We add water. Okay, now how much water do we add? That depends on how much we're using of this and how much we want to make of this. And we have a magical little equation that allows us to be able to do that calculation. M1V1 equals M2V2. Notice this is capital M, which is the same M we're using for molarity. Where do I use that? Right here. Capital N is a symbol for molarity. Okay, notice it's also my unit for molarity. It means moles per liter. So moles per liter times volume equals moles per liter times volume. Why does this work? Well, if I take a huge scoop of Kool-Aid and put it in water and I realize it's too concentrated, so I add water to dilute it, did I change the amount of powder that I originally had in solution? Well, no. All I did was spread out the powder in solution. I just made this powder more spaced out. So if we do this math, moles per liter is molarity, volume is liters, equals moles per liter, molarity 2, times liters. Our liters cancels out, and what we're basically left with is the amount of moles on each side of this equation are the same. And that's because that's exactly what it is. I'm not changing the amount of moles of hydrochloric acid I start with. I'm just changing how much volume those moles are in. So that's how this equation is actually working. So this is how I would do this problem if I was making a lab for you guys. So let's say I knew I needed to make 100 milliliters of 1 molar HCl from a 10 molar solution. Okay, so what would I do? It doesn't actually matter which one's M1V1 or M2V2 as long as they go together. In other words, I have 1 molar and I want 100 milliliters of that 1 molar solution, so they could be M1V1 or those could be M2V2. That's kind of up to you. I know yesterday that wasn't actually explicitly said, so that could be a little bit confusing. So let's just say M1 is 1 molar, V1 is 100 milliliters, because that's how much volume I need of my 1 molar. Well, the molar I'm starting with is 10 molars. How much volume of that do I need? Okay, so it's basic math. We end up with 1 times 100, which is 100, divided by 10, which is 10. So I need 10 milliliters. And actually, in terms of sig figs, that should probably only be 1 sig fig, so we'll just leave it as that. And that's kind of my fault for using weird numbers like I did. But regardless, I need 10 milliliters of my 10 molar to make 100 milliliters of my 1 molar. What does that mean? Well, that means if my final volume is 100 milliliters and I only am using 10 milliliters of the 10 molars, I have to add 90 milliliters of H2O to dilute this 10 molar solution to 1 molar. Okay, let's look at another problem very quickly. I am running out of time on the video. The videos only allow me to do about 15 minutes at a time. So let's say we have a 14.9 molar NaCl solution. And let's say we have 25 milliliters of this. 25 milliliters of 14.9 molar solution, and we want to make a 1.67 molar solution, SOLN is solution. I want to know how much water did we add to dilute it, basically. Okay, so first off, M1V1 equals M2V2. Well, I'm starting with 14.9 molar and 25 milliliters. Now, the beauty of this equation is I don't actually have to convert to liters to be able to do it, as long as I recognize that whatever volume unit I use on this side, I have to use on the other side too, or that's what I'm calculating. So M1's 14.9, V1 is 25 milliliters. Again, that could be M2 or V2 as well if I decided to do that. It doesn't actually matter because it's the same math regardless, as long as these two numbers are actually going together. From there, we have 1.6 molar. That's going to be our M2. Okay, and my smartboard just lost it. Give me a second. All right, there we go. Sorry about that. So my M2 in this case is 1.67. And I'm calculating my V2. So I end up with 14.9 times 25 divided by 1.67. And what I end up with is my V2 with 2 proper sig figs, because I only use 25 versus 25.0 here, would be 220 milliliters. So because I use milliliters here, I have to use milliliters here. Now, how much water did I add? Well, this is my final volume. This is how much I originally had. So 220 minus 25 is going to give us 195 milliliters of H2O added. All right, that's it. Check your work. Let me know if you have questions. Thanks, guys. Bye.